Hey everyone, and welcome. I am so incredibly excited to guide you through this explainer today. We're going to be taking a really structured journey of discovery through the dynamic and honestly totally fascinating worlds of physics and earth science. We are going to break down some seriously complex phenomena into clear, digestible insights. So get ready to see the world around you in a whole new light.
All right, so here's our roadmap for today. We'll kick things off with core physics and earth concepts, then we'll smash some common science myths, move into mastering science with math, look at models and scientific methods, and wrap it all up with some highly effective tips for science success. Let's get right into it.
Okay, Section 1, Core Physics and Earth Concepts. So, let's start right beneath our feet. When we talk about tectonic plates, we aren't just talking about the crust. A tectonic plate is actually the entire solid outer layer of the Earth. That means it's made up of both the crust and the uppermost part of the mantle. And here is the really amazing part. They move because of flow happening down in the more viscous, lower part of the mantle. We're literally standing on massive shifting puzzle pieces. Now, if I asked you what gas you're breathing mostly right now, you'd probably say oxygen, right? Well, clean, dry air is actually a massive 78% nitrogen. Oxygen makes up just 21%, with other gases like carbon dioxide making up just about 1%. It's a great reminder that our environment is often composed a lot differently than our basic intuition suggests.
Okay, zooming out from Earth to fundamental physics, there are three absolute bedrock rules that dictate pretty much everything happening around us. First, energy is conserved. It cannot be created or destroyed, it only transfers forms. Second, sound travels as longitudinal waves, meaning it desperately needs particles to vibrate. It absolutely cannot travel in a vacuum. And third, gravity isn't just about the Earth pulling you down to the floor. It's a force of attraction between any two objects that have mass. Everything pulls on everything else.
Moving right along to Section 2, Bashing Common Science Myths.
You know, it makes total intuitive sense to think a heavy bowling ball would hit the ground way before a feather. That's just our everyday experience. But in a pure vacuum that's totally devoid of air resistance, gravity pulls all objects at the exact same rate. In the real world, a feather only falls slower because the air particles are physically pushing back against it. Take away the air, and mass doesn't change the speed of the fall one bit.
And that actually brings us right back to our rule about sound waves. Despite what those epic sci-fi movies show us, with the roaring spaceship explosions, sound waves absolutely require physical particles to carry their energy. Because outer space is essentially a giant vacuum, there are no particles to vibrate. So in reality, a massive space explosion would be completely, totally silent. Hollywood has kind of been lying to us.
Here's a huge one about our oceans. A lot of people assume the Earth's rotation just sort of spins the water outward to create tides, but the fact is, tidal forces are actually caused by lunar and solar gravity. The moon's gravitational pull on the Earth literally creates bulges in our oceans on the side closest to the moon and on the exact opposite side too. It is this amazing gravitational dance between the Earth, moon, and sun that creates the daily tides.
Okay, let's get super precise with our language here. How many times have you heard someone say, well, heat rises? Scientifically speaking, heat itself doesn't actually rise. It's hot fluids and hot gases that rise. When a fluid or gas is heated up, its particles gain kinetic energy, they bounce further apart, and they become less dense. And because they're less dense, they naturally float upward, which creates a convection current.
All right, up next is Section 3, Mastering Science with Math.
Look, math is what makes all these abstract concepts totally tangible. When we want to really nail down how motion works, we use the basic speed formula. Speed equals distance divided by time, usually measured in units like meters per second or kilometers per hour. It's a beautifully straightforward equation that completely unlocks our ability to predict and analyze motion.
But let's pause and think critically for a second. Ask yourself this. If you go for a run, stop for a quick water break, and then start running again, how exactly do we use math to describe your overall speed? The basic speed formula works flawlessly for a constant, steady pace, but real life is messy. How do we account for those periods where you aren't moving at all?
Well, by tracking total distance over total time, we can pinpoint the average speed. Think about a runner's journey. At 10 seconds, they've covered 50 meters, meaning an average speed of 5 meters per second. But at 20 seconds, the distance is still exactly 50 meters. They stopped. Yet, by taking the absolute total distance at the end of the run and dividing it by the total time it took, we get an elegant mathematical summary of a really complex start and stop journey. That brings us to Section 4, Models and Scientific Methods.
Because we can't exactly crack the Earth open to look inside, scientists rely heavily on models to understand massive or invisible forces. Imagine taking some thick syrup, cooling it in a beaker, tossing a broken biscuit on top, and then applying heat from underneath. The syrup acts just like the flowing mantle, and the heat creates a convection current. As the warm syrup rises, it literally pushes the biscuit pieces, our crust, apart. It's such a brilliant, everyday way to visualize divergent plate boundaries.
Now, a huge part of the scientific method is allowing our theories to evolve when new data drops. Take the moon's formation, for instance. We started with the capture hypothesis, wondering if Earth's gravity just sort of caught a passing rock. Then the accretion hypothesis suggested Earth and the moon formed side by side. But eventually, hard evidence, like moon rocks collected from the Apollo missions that showed a previously molten surface and specific isotope ratios, pointed us firmly toward the giant impact hypothesis, the idea that a Mars-sized object slammed into early Earth. Science adapts when better data arrives, and that's its superpower.
And finally, let's wrap things up with Section 5, Tips for Science Success.
If you want to truly succeed in studying these concepts, you really have to think like a scientist. First off, always lock in clear predictions before you run an experiment. Second, ruthlessly check your data reliability by using large sample sizes and repeating your tests. Third, be on the active lookout for anomalous results. Those weird, unexplained outliers are usually what lead to massive new discoveries. And finally, always evaluate your secondary sources for potential bias to ensure your conclusions are actually solid.
And here's a really vital piece of perspective to keep in your back pocket. Scientific theories are almost never accepted overnight. They require a massive body of evidence and rigorous, sometimes grueling peer review. Remember our tectonic plates? It literally took decades for that theory to be accepted by the broader scientific community. Have patience with the process of discovery, both out there in the scientific world and in your own personal learning journey.
As we wrap up this explainer, I want to leave you with a bit of a challenge. Look around your everyday world and ask yourself, what other phenomena can you completely demystify using these core scientific models and math skills? Whether it's the weather patterns outside, the architecture of your city, or even just the technology sitting in your pocket, the tools of physics and earth science are everywhere, just waiting to be applied. Keep questioning, keep calculating, and definitely keep exploring. Thanks so much for learning with me today.